In this section of video, we will look into the problem of force convection heat transfer in a circular tube of capital radius r. In this problem, a viscous fluid is flowing in a pipe at an inlet temperature of T1 and with constant density rho, thermal conductivity K and viscosity mu and heat capacity Cp cap as its properties. The flow in fluid is assumed to be laminar and there is constant radial heat flux Q naught is given to the wall of pipe using electrical heating. In this problem, we need to develop the equation for temperature profile and give the value of Nusselt number in this case. So to solve this problem, we need to have certain assumptions. First one is the flow in pipe is laminar, therefore it is a one-dimensional flow, and thus we will take the change of velocity in that direction with respect to r only, and we assume that Vr and V theta are assumed to be 0. Now there is constant radial heat flux at the wall is given, which is Q naught, and temperature at the surface of the wall is assumed to be T naught. Now constant pressure gradient is assumed along the z-axis, which will be a function of z. Therefore, P is equal to P of z. And due to the large length of the pipe with respect to r, the end effect has been neglected in this problem. Now, to solve this problem of force convection heat transfer, we need to calculate the velocity profile in the system. But from the knowledge of the momentum transfer in flow through pipe, we already have velocity profile in flow through pipe, which is given by Vz equal to P naught minus PL r square upon 4 mu L into 1 minus small r upon capital R square. Now we know that at r equal to 0, Vz is equal to maximum at the center of the circular tube, therefore, which is nothing but P naught minus PL r square upon 4 mu L is Vz maximum. Substituting this in equation and rearranging Vz, we get Vz equal to Vz max into 1 minus r upon capital R square, which is equation number 1. Now in this problem, heat is being transferred in both r and z direction. Therefore, we assume temperature as a function of r and z, that is T r comma z, is equal to C naught z plus f of r. Now, to solve this problem, we need to consider energy balance for the differential shell of washer shape system. Now, for this washer shape system consists of delta R and delta Z thickness, and it is the intersection of annular region between this delta R and delta Z thickness differential cell. A shell energy balance equation is given by rate of combined energy flux in, rate of combined energy flux out, plus rate of work done on system by external forces, and rate of energy production. This all should be equal to 0. Now, if you look, the total energy in at R is given as ER into R is 2 pi R into delta Z, that is the inner surface area of this differential shell, and total energy out at r plus delta r is er at r plus delta r into 2 pi r plus delta r into delta z, that is the outer surface area of this differential shell. If we assume that delta r is negligible, then this equation reduces to 2 pi r er at r plus delta r into delta z. A total energy in at z is given as Ez at z is 2 pi r into delta z, is the upper surface area, and total energy out at z plus delta z is Ez at z plus delta z into 2 pi r delta r, that is the downward surface area of this differential shell. Now work done on the fluid by gravity is given by rho into volume, that is 2 pi r into delta z. This is the volume of the differential shell, which will give us mass into Vz into Gz, will give us work done on fluid by the gravity. Now here, as this is a steady state system and there is no rate of energy generation, therefore we take rate of energy production as 0. Now in this schematic diagram, you can see the clear picture of this flow through pipe and differential shell. Here you can see that the upper surface area is given as 2 pi r into delta r, and the outer surface area and inner surface area is considered to be 2 pi r into delta z, and Ez and Er are the combined energy flux flowing through in and out of the system. Now, substituting these equations in the cell energy balance equation, we will get 2 pi r er at r into delta z minus 2 pi r er at r plus delta r into delta z plus ez at z 2 pi r delta r minus ez z plus z 2 pi r into delta r plus the work done by the gravity will be equal to 0. Now, when we divide the whole equation by 2 pi into delta r into delta z, we get minus r into er at r plus delta r minus r er at r upon delta r and minus ez z plus delta z minus ez z into r upon delta z plus rho v z z into r equal to 0. Now, using the definition of differentiation, as the limit tends to delta r and delta z tends to 0, we will get the partial differential equation minus 1 by r del r er upon del r minus del z upon del z plus rho vz into z equal to 0. This is our differential equation for the system. Now, using combined energy flux vector for r and z component and for non-zero component of velocity, we will get Er is tau rz into Vz plus Qr. As we know, this is a tau rz into Vz is the tau rz into Vz is given as the convective energy flux and Qr is the conductive energy flux. Using Newton's law of viscosity definition, we will get minus mu into del Vz del r into velocity z, and using Fourier's law of heat conduction, we will get Qr equal to minus k del T upon del r. Same for combined energy flux in that direction, we will consider the kinetic energy flux along with the internal energy flux, which by replacing with enthalpy, we will get this particular expression. And for convective energy flux, this is 2 tau zz into Vz, and conductive energy flux in that direction is given as Qz. Substituting the definitions and substituting Newton's law of viscosity, we get this particular definition. Now we will simplify the equation 2 by using a partial differential definition. We'll get minus 1 by r into r del er upon del r plus er minus del z upon del z plus rho into vz into z equal to 0. Substituting this flux expression in the above equation, we will get this particular expression. And after rearranging the equation and omitting out the non-zero components, we will get this particular equation. Now, in this expression, we can omit some brackets by taking some assumption, like as viscous heating is neglected in this problem, mu into del Vz upon del square equal to 0. Therefore, this term becomes 0. Okay, this term becomes 0. Now, as heat conduction in the axial direction is negligible in comparison with the heat convection in the axial direction, therefore, we will not consider the axial heat direction, conduction in axial direction. Therefore, this term del square T upon del Z square will be equal to 0. Now, from the momentum transfer knowledge, we can get the z equation of motion as this particular expression, and after substituting uh, the zero components, like in first case, as it is a steady state system, this term becomes 0, del Vz upon del T becomes 0. As there is no Vr velocity, therefore this term becomes 0. As there is no v theta velocity, therefore this term becomes 0. And as the velocity is not changing with respect to r, therefore this term becomes 0. So therefore whole left side will become 0 after substituting this assumption, and that equation of motion reduces to this particular equation. This particular equation comes when we substitute this further, like in del p upon del z, this term will be non-zero, but here del vz upon del r, this term will also be non-zero, But as the velocity is not changing with respect to theta, this term will be equal to 0, and velocity is not changing with respect to z, this term will be a 0. Therefore, by substituting this assumption, we get that equation of motion reduces to this particular 0 equal to minus del p upon del z plus mu 1 by r del upon r del v plus rho g. Now, applying these assumptions and equation in equation number 3, we will get this particular equation as this term becomes 0 by substituting z equation of motion term, and this is neglected, and this term is also 0. This equation will reduce to rho cp cap vz into del t upon del z, which is equal to k into 1 by r del of del r into del t upon del r. Now substituting Vz from equation 1, we will get rho Cp into Vz maximum 1 minus R upon capital R square into del T upon del Z equal to K into 1 by R del upon del R into del T upon del R. Now, if we look into the boundary condition, so there are three boundary conditions for solving this equation. Boundary condition number 1, at r equal to 0, t equal to finite. Boundary condition 2, at r equal to r, k into del t upon del r equal to q naught, which is constant, as the constant radial heat flux is provided at the wall. Therefore, this assumption is taken into account. And boundary condition number 3, at z equal to 0, t is equal to t1. Now, to reduce the parameter and solve this problem, we will put this problem into the dimensionless form. This dimensionless selection is arbitrary, and it is assumed by looking into the terms of the problem, like theta is equal to t minus t1 upon q naught r by k. These assumptions come from the boundary condition number 2 and 3. Considering boundary condition number 2 and 3, we get this theta equal to t minus t1 upon q naught r by k. This dimensionless parameter theta, xi is given as r upon r, as r upon capital R is there in the expression. Therefore, we choose I is equal to small r upon capital R. And zeta is what? Zeta is the axial coordinate, which is chosen as z upon rho Cp Vz maximum into r square by k. Now, to substitute these differential parameters into equation number 4, we need to differentiate this with respect to theta and dt to substitute this into equation number 4. By performing this calculation and substituting in equation number 4, we will get this particular equation, that is rho Cp Vz max 1 minus z square into d theta q naught r upon k into rho Cp V max r square by k d zeta is equal to k into 1 by r del upon r into del theta into small r into del theta q naught r by k upon r into del theta. So substituting this and performing calculation and cancelling the terms, we get this particular equation reduced to the 1 minus zeta square del theta upon del zeta equal to 1 by del zeta del z into del upon del z into z into del theta upon del z. So this gives us the dimensionless equation. Now here we need to check for this three boundary condition in this differential equation by performing by substituting this equation in this boundary condition in this. For boundary condition number 1 state that at zeta equal to 0, theta equal to finite. Boundary condition number 2 is at zeta equal to 1, del theta upon del z equal to 1. And boundary condition number 3, at zeta equal to 0, theta is equal to 0. Now we will look into complete calculation in the next part of this video.